Okay, so in the last video we looked at how we could use root to store quantities into a histogram. So in that case we used it to store the spectrum of secondary electrons which were created, and we just used the Geant4 analysis root or G4 root functionality to create a histogram in this method here. So let's just and in the stepping action, we stored the kinetic energy into the histogram. So in this video, I'm just going to show how we can plot this and convert it into a format which you're more, well, I'm guessing you're more comfortable with, and you can edit the data a bit more easily. So I just want to show one thing. So in between the last video, I created a 2D histogram to also show how to create a 2D histogram. So the only difference between the 1D and the 2D is you use the create H2 for 2D histogram, and instead of just having the number of bins and the minimum and the maximum, it's now the number of bins in the X and the min and the max range of the X, so minus 50 to 50. Then we then put the number of bins in the Y direction, or number of Y histograms, and then again the min and the max range. And I've also added the functionality to return the ID of a histogram, so just get H2 ID, or if we wanted to get the ID of this H1 or the 1D histogram, or this H1, then we'll just change this to H1 and get the get ID. So you might remember I mentioned that when we are retrieving or filling the histogram, we can either enter the ID of the histogram, and this is IDs assigned based on the order when it's created. So for this case, this histogram was created first, so it had an ID of 0, but we can also use it based on the name that we give it, and in this case, H1. So we could also store it by getting its ID from the name of it. So in this case, I've just, in the stepping action, I've added this 2D histogram to be filled using the functionality of get H2 ID. So in this case, I'm returning the H2, so the ID number of the H2, which will just be 0 because it's the first 2D histogram. But if we were to create if it were a 1D histogram, then it would be the second 1D histogram. So then it would have an ID equal to 1. So I should probably point out what the 2D histogram is storing. So I'm just storing the position and where electrons are created. So I've just added this under our 1D histogram, and so now it's storing the position where the secondary electrons are created. And instead of using MeV, I've naturally given it units of centimeters. And the reason why centimeters and not, say, millimeters is just because, remember, our world histogram is 100 centimeters cubed, and I've got 100 bins, so the range of minus 50 to 50, so for every bin, there'll be 1 centimeter range. So if we just compile this code, and if we just run it with the good old run electron macro, so edep run electron, and we've still just got it set to 100, then we'll get our good old 330 created and mean energy. So last time I showed you how to see the results interactively of the root file. So you can just launch root and -L for no logo, and we can start a new T browser. which will just create a file browser that we can see the files output. So if I just make that a bit bigger, we can go to our basic output. So 1D, we saw it last time. And then for our 2D, then I'll just change this to a coals and press it again to get some color. So this represents the number of electrons created at a certain position. So remember, our beam's generated at -50 in the X and 0, 0 in the Z. So this is where our beam is generated, and it goes towards the right. So as you would expect, we've got all our electrons generated around, well, most of them being generated. Oh, actually, I'll just zoom in slightly. So we've got our 1 MeV electron beam being fired, and it's just a point beam. So it hasn't got a size associated with it per se. And let's just, it's a bit sluggish because of being off campus. So here's, you can see we've got most of the secondary electrons being created near the expected trajectory of the beams, but it might also scatter here and create electrons here. Like it might go through multiple scattering and be deflected in this direction, but these are also probably just secondary electrons which are created from other secondary electrons. So we might get a secondary electron created here from the primary electron beam, and then it would go in some direction, and then it might then create another secondary electron here through ionization and so on. So it's all good, but how can we extract this data and edit it or analyze it in a method you might be more used to, such as just using Excel instead of Root? So you can just quit that. And so if we list the contents of the directory, you'll see these .c files which I've included. So if I just go ls.c, we've got these 3 different macros. And if I open, let's say the plot Angie spectrum, then you can see the contents of this macro. So you can read the comments here. So it opens our root file, which we created. So the name's here, basic output.root. And then you see it's creating a histogram called H1. And then it gets the histogram H1 from the file and puts that into memory. And then I've got some plotting options here. And then if you want, you can save it, or it'll just, by default, it'll be displayed at a size of 800 by 600 pixels. And here's just some axis options here, which you can edit around. But probably the thing you most care about is these lines here, where we've got a OF stream out file. So what this does is it just converts the root histogram file format into just a text file. So it just saves it to a text file, giving this name here. So in this case it's 6 MeV, but we should probably just change that to 1 MeV there. And instead of depth, edepth, let's call it 1 MeV secondary electrons. Save that there. And so what this is doing, it's just looping over the bins. So the number of bins in the 1D histogram. So remember that in our run action, we assigned it to have 100 bins between 0 and 1. So unlike with standard C++ arrays, which the first entry is a 0, and so you're probably used to having the for loop starting at 0 and then going, instead of less than equal to's, it just goes to less than. But with root, their histograms are, the first bin has an ID of 1, and so that's why we start at an ID of 1, and then go less than or equal to 100, since the 100th bin will have an ID of 100. And then there's also a bin 0, and this will just have underflow and overflow, but you don't need to worry about any of that. So that's this probably the most important part of the macro that you care about. So you can change the name here of the output file. So let's just open root again, and if we want to execute root macro, we can just go .x for, if you like, I like to think of it as execute. And so then we just give it the file name, and just like with the standard terminal, we can also use the tab and see the options we have to execute. So we want to use the plot energy spectrum macro. So if we just go .x plot energy spectrum.c and run that, and this will take a while because I've got it being plotted. So we've got the relative number of counts at each energy. So if we just close that, and if we wanted to quit root, we just go .q for quit. And if we just list the most recent files, we see we've now got this 1 MeV secondary electron. So if we wanted, we could just quickly scroll through it with less and see the counts in the bins. Or let's just, if we just refresh this, we can just view it here. So you see we've got our central bin value. So this is 005 MeV, and the number of electrons within this energy range of, in this case, it would be 0 MeV to 0.01 MeV, since the bin width's 005. 100, 1 MeV, 100 bins. So sorry, 0.01 MeV. And so then you've just got this output, and then you can just put in the Excel if you want to do anything with it. All good. And I'll also just plot the show the 2D macro. So what is it? Plot 2D fluence. I think I've got it. So this won't create an output file. You can create it, convert it to an output file, but don't need to. So compared to what we had when we did new T browser, we've changed the scale to have a log. So now we've got a slightly different color scheme, and that's that. So that's just how you can run the root macros and extract the information from the root files into a text file, which you're probably a bit more comfortable to use. And that's that.